So this time what I'm going to take us on is comparing two samples. So rather than comparing against some fixed level, we're going to have two different groups that we want to compare. So the thing that we need to be aware of for this is that when we compare two groups, there are actually two different t-test formulas. I'm not super troubled about us knowing that, the ins and outs of how we actually calculate these formulas, but I am interested in us knowing that in terms of a decision-making process, if we want to conduct a t-test, we need to know whether the variances of the two groups are, it's plausible that they're equal or it's not plausible that they're equal. So there are two different t-test formulas that we use. I would like us to be aware of the process of decision-making. So we need to know which formula to use. We have software to solve this stuff. There's no real point in deriving the formulas for both cases. So what we're going to need is, when we want to compare two groups, we're going to need some additional test to decide which t-test formula to use. So the test that we use is called a variance ratio test, and this is going to be, this idea of testing for equal variance is going to be a recurrent theme in what we do. So let's have some context. Again, we're having an example on this. It's about energy and pollution. So energy and pollution, let's continue to talk about coal. So there are some ideas. I've picked on China here, but we know if you're following the press that this is equally relevant for discussions in India. So there's some sort of discussion that says, hey, look, the coal in Australia has a high energy content, and that if we were able to sell, if we in Australia mine coal and send it to mines overseas, that this will stop them having to mine less high energy content coal and burning that. And so the net impact of us mining coal will be that globally there will be less global emissions from coal, because the coal that will be powering these power stations will be relatively energy dense. This is actually not an unreasonable proposition for people to take. It's actually something that we might really want to think about and say, okay, we really do have coal-fired power stations. We're going to continue to have many coal-fired power stations. What is the best way to run those power stations? So we've got our different kinds of mines. So here I've got the coal coming out of an underground mine in China, and here we're working with an open cut mine in Australia. And the proposition is that it would be good for us to expand coal production, because on a global level, that coal that we produce here would displace some low energy content coal, and that would give us a net CO2 emissions gain. All right, it's a reasonable proposition to want to test. Let's think about how we test this. Should we be expanding coal mines in Australia, or should we not be expanding coal mines in Australia? Okay, so to a certain extent I've made up this data, but the values I use are representative of what you find in the real world. So I've got two data samples here. So one set of data from coal mine in China that we are theoretically going to displace by expanding coal production in Australia, and the other samples are from Australian mine. We might imagine that realistically this is a mine on the east coast. The coal we have here in Western Australia is not so high quality, so we wouldn't be wanting to expand that. But there is an active debate about the Galilee Basin in Queensland. Okay, so what do we want to do? So we've got this sample data, we want to test it. So how do we do that? So we would read in our data into R. So if I just get my little red pointer happening over here, so this is my object, this is the name that I give my work in R. I use the function read in the data, and this is the sample data file that I have. And remembering that we're just having our Excel files with the .csv extension. So I'm going to get the data into R. I'm going to apply the structure command to make sure that I know what I'm seeing with the data, and I might also apply the summary command. And if I did that, you would see down here, so this is when we apply the structure command. What does it say? It says that I have data. These are the samples. Okay, so I've got 100 observations. So I have 100 samples from Australia and 100 samples from the China mine. And these are all integers. And then I could see that it's given me the summary and what I can see down here from the mean. So this is the mean of the China sample. This is the mean of the Australian sample. So you can actually see that on this sample, the energy density in kilojoules per kilogram of coal is a little bit higher in Australia in China. And so we would want to be testing the proposition formally. Is that difference in the means just due to sampling variation? Because remember, we don't have the population, we just have a sample. Or is that a real difference, that the population of coal here is different, and in this case, a higher energy content? So it's the claim being made on this sample is plausible. We want to have a formal test of that. We would have a box plot of the data, and this is what it looks like. So again, you can see these are the sample measurements, and you can see these are clustered a little bit lower than here. It looks like there might be a difference. For me, there's still some overlap here, so I'm actually not convinced that there is a difference, but we're in a plausible space. So this is the box plot is a good representation. It's giving us an idea of what's going on with these two samples. What are we trying to do formally? So formally, we have a situation like this. Here is my mean for the coal from China distribution. Here is my mean from the Australia sample, and you're trying to determine, are these two means drawn from a common population? I've also got here the standard deviation. So these are the variances. So the variance for the coal sample is a bit smaller than the Australian sample. So when the variance is larger, remember that means that the spread of the data is larger. So that's what I'm sort of showing you here. So that's sort of a stylized representation. For these samples, I actually calculated the empirical smooth distribution for these two data samples, and this is what it looks like. So for our t-test, this is the distribution, the smooth distribution for China. This is the one for Australia. So you can see that the mean, so around about here for Australia, and the mean around about here for China. So the mean sample for the Australian one is a bit higher, but it's actually more spread out. So these are our guesses of what the population looks like. So if we say we have a sample, and from the sample we have a guess of what the population looks like, that's my guess of what the population of the coal energy content distribution looks like in China. This is my guess of what the coal energy content distribution looks like in Australia. For the t-test, the formula we use is if the variances, so the spread, if the spread is the same, we have one formula. If the spread is different, we have a different formula. And like eyeballing this, you could see that this, for me, they look different, all right? But we can't, we like to have, for me, they look different. For someone else, they might not look different. So we remove that sort of subjectivity from the visual plots, although I find them very effective, and we look at them in terms of a formal test. So the formal test that we're going to use, and remember this is a test just to decide which t-test we're going to use, is called a variance ratio test. And what you do is you just divide one by the other. So if you divide one by the other and they're the same, the ratio will be 1, okay? And we decide near and far from 1 using our formula. Now, the convention in tests is always to put the highest value in the top, all right? But you don't actually have to do that. There's no reason that you couldn't do it. The test works exactly the same if you put the high value at the bottom. There's no problem in doing that, but the convention is usually to express the test this way. So you divide the high one by the low one, and is that number far from 1? Now, it turns out that we divide those values, we have a distribution just like we have for the t-test. This one is the F distribution, and it gives us the same sort of thing. We have this do not reject zone, so that the space of do not reject that the variances are equal, or that we are sufficiently close to 1 to not worry about the difference, or that we're far away from 1. And you can see I'm just sort of identifying that depending on which way we set up the test, we could be looking for numbers very close to 0 to reject the null, or numbers very far from 0. So if it's 1, remember, if they're the same, the ratio would be 1. If the ratio is not, if they're not the same, the ratio will be far from 1. And that's really what we're doing. So we formalize this. So this is before the t-test. the variance for group 1 is the same as, the variance for group 1 is the same as the variance for group 2. So how would you write that? I'd just go for words for this one. You can use the formal notation if you want. The alternative is that the variances are not the same. We have the alpha at 0.05 to formalize our test, and we're going to apply a p-value decision rule. So you'll see that this is no more complicated than implementing a t-test. What do I have up here? I have with the data that I've got, so my coal data, apply, instead of t.test, it's var.test, and these are the two groups. So these are the variable names in my data matrix. So we know what a data matrix is. These are the variables. We can see that the p-value much less than 0 reject the null. So, just conceptually, what would happen if you framed the test the other way? And what we see is if we just look at the p-value, it doesn't matter. So whether we put the small value first and then the big value, or the big value first and then the small value, it doesn't matter as long as we apply the p-value decision rule. Whichever way we conduct the test, it's the same p-value. So that means that we can just implement this test without really thinking about it. It's just var.test, group 1, group 2, apply the decision rule, p-value less than 0.05, reject the null. If it's greater than 0.05, do not reject the null. So that's what we've done. So we know that we need to, in this case, use the unequal variance formula. So here is my two sample t-test. So remember, the mean of group 1 is the same as group 2. So you can always get, to get started, you can just have these formulaic setups that are just the mean of group 1 is equal to the mean of group 2. Of course, we know that what we're talking about is coal energy density in Australia and coal energy density in China. But if you don't want to, think about it too much and you just want to get started with this kind of stuff, mean of group 1 is equal to the mean of group 2. That will be fine. We're going to conduct the test with the unequal group variance formula in R, and we're going to apply our decision rule. So two sample t-test, what are we talking about? Are the calorie content the same in these two samples? The samples are informing us about the populations. We're interested in the populations because we're interested in how much coal we burn because of the emissions that are going to come from that. So, we're not really going, oh, gee, I woke up this morning and I felt like conducting a t-test. No, we're actually interested in looking at a question, and these are questions that are out there in public. Should Australia be expanding its coal mines? These are propositions that are put in the public debate at the moment, and we might be interested in testing these propositions. So here we have, how do we implement our t-test? With the data, so that's what we've read into R, apply the t-test, variable name 1, variable name 2, variance equal false. All right, so we have to have this little setting in here. So it's not that, we have to type some values in R, but it's following a pretty fixed pattern with the data set. Okay, so that's your data matrix. Apply the function. The function you want to apply is the t-test. Apply it using the variables that we have specified. And what type of t-test? The type of t-test where we have unequal variance. And we just look at the output. P-value is less than 0.05. Draw your attention. So these are the two means. Or we actually know that this is the mean for the Australia sample. This is the mean for the China sample. So these means, it just gives them, it doesn't pick up, Australia and China, but that's group 1, which is X, and that's group 2, which is Y. So the way that we put the values in here matches the way that it's going to give them down here. So we've rejected the null that the two samples are the same, and we know from down here that the energy content of the Australian sample is higher than the energy content of the China sample. Now, so which means that the energy density of the Australian coal is higher. Now, we've found a statistically significant difference. That is not anywhere near the endpoint. We need to know, is that difference important, right? So is a difference of this size practically important, okay? So we need to know that by referring to environmental significance dollars if we're in the more looking at the social sciences, or biological conditions. So we need to, go on to a whole lot of other steps before we could conclude that finding a statistically significant difference is actually useful for anything. And that's an opportune time for us to have a break.